Hello there, my amazing people, students, subscribers, and all the lovers of chemistry out there. I'm super excited to be here with you today again. It's always a delight for me whenever I have the opportunity to engage with you on this space where we get to break down chemistry, take the mystery out of it so chemi can make history. Today we have something very special that we want to deal with in this series of gas laws that we've been handling for a while now. And today we want to talk about the concept of ideal gases. And that brings us to the ideal gas law, which says PV is equal to nRT. So without wasting time, let's get into the details of what we have and see if we can treat one or two questions to consolidate your understanding. First things first, what is the ideal gas law? The ideal gas law is actually an equation that shows the relationship that occurs between pressure, volume, temperature, and the number of moles of a gas. So we saw some gas laws in our previous videos that showed the relationships that occurred between some variables. For instance, Boyle's law. Boyle's law showed the relationship that occurred between pressure and volume. We saw the Charles law, which showed the relationship that occurred between volume and temperature, and so on and so forth. Now, today, what we're looking at is the ideal gas law. It is an equation that shows the relationship that occurs between pressure, volume, temperature, and the number of moles of a gas. And it is written as PV is equal to nRT. All right, so here are the definitions of all the variables we have in this formula. First of all, we have P. P stands for the pressure of the gas, and it is usually measured in atmospheres or pascals. V stands for volume. The volume of the gas is usually measured in liters or meter cube. M here actually stands for meter. So m raised to power 3 refers to meter cube or cubic meters, whichever one you choose to call it. N here stands for the number of moles of a gas, and then R here stands for the ideal gas constant, and finally T here stands for temperature, which is measured in Kelvin, not degrees Celsius, always measured in Kelvin. So having said all of that, there is one variable among all of these that stands out particularly, and that is the ideal gas constant. We want to talk about what it means, and we want to talk about its value. So before we do that, let's break down the formula one more time. P stands for pressure, and pressure here refers to how much force the gas particles are exerting on the walls of the container. V stands for volume, and the volume refers to the amount of space the gas occupies. Remember, matter is anything that has weight and can occupy space. The space in this context is referred to as the volume of the gas. And then N stands for the number of moles, which refers to the amount of the gas present. T stands for temperature, and temperature refers to how hot or cold the gas is, and it is measured in Kelvin. And then finally, R stands for the ideal gas constant. It is a fixed value, or it has a fixed value depending on the units used for pressure, for volume, for number of moles, and for temperature. So having said all of that, let's talk about the ideal gas constant, R. So that brings us to this next thing that we want to say. The ideal gas constant actually has different values, and it depends on the units used in the gas law equation. Just like, for example, in today's world, we have different types of cars. There are cars whose speeds or speedometers measures their speed in miles per hour, mph. Other ones have their speed measured in kilometer per hour, right? But in this case now, we want to see how the ideal gas constant has its valued measured, and its valued measured is dependent on the units that we used for pressure. For instance, look at this. When pressure P is measured in atmospheres, volume V is measured in liters, and temperature T is measured in Kelvin, R has the value of 0.0821 liter atmosphere per mole Kelvin. I hope you can see how that works. Now you can see when pressure is in atmospheres, volume is in liters, temperature is in Kelvin. The unit that we use to measure the ideal gas constant contained liters, contained atmospheres, contained moles, and it contained Kelvin, which corresponds to all these units that were mentioned. So you can see the importance of making sure that your units are uniform, all the steps that you take and all the way. So now the next thing is when pressure is measured in pascals, volume is measured in cubic meters, and temperature T is measured in Kelvin. The ideal gas constant is 8.314 pascals cubic meters, I beg your pardon, Pascal cubic meters per mole Kelvin. So that's it for the ideal gas constant and the values that it represents. So having said that, let's see if we can solve for the other variables. Now, remember the ideal gas equation says PV is equal to nRT. So for instance, if you are asked to find P, it means you must make P the subject of the formula. To do that, you divide both sides by the coefficient of P, which in this case is V. So when you do that, V cancels V, and then P is equal to nRT over V. That is why we have this formula. When you are asked to find P, it is nRT over V. The same thing goes for V. When you have PV is equal to nRT and you are asked to find V, you divide both sides by its coefficient, which in this case is P. P cancels P over here, and then V is equal to nRT over P, which is what we have over here. The same thing applies for N. When you have PV is equal to nRT and you are asked to find N, you simply divide both sides by its coefficient, which is RT. And when you do that, you are left with N is equal to PV over RT. And that's what we have over here. And then finally, when you want to look for T, the temperature PV, which is equal to nRT, says you need to divide both sides by the coefficient, which in this case is nR. nR cancels nR, and then you're left with T being equal to PV all over nR, which is what you have over here. So that's it for finding the other variables in the ideal gas law. So can we solve some questions? Yes, so let's get into solving some questions. So the first example says a football has a volume of 0.5 liters and the air inside is at a temperature of 295 Kelvin. The football contains 0.02 moles of air. What is the pressure inside the football? So let's go ahead and list out our variables first things first. So we have PV, which is equal to nRT. P here stands for pressure, and the question says what is the pressure inside the football? So we do not know. All right, and then we have V, which is the volume. V says that the volume of the a football has a volume of 0.5 liters, so we have 0.5 liters. N stands for number of moles, and we have 0.02 moles of air contained, and then R is the ideal gas constant. Now in this case, volume is measured in liters, N is measured in number of moles, P will be measured in atmospheres definitely. So we have 0.0821 liter atmosphere per mole Kelvin. So the next thing to do is to see the temperature. The temperature is 295 Kelvin. So let's impute our variables. But before we do that, we are asked to find pressure. So to find pressure, we make P the subject of the formula. And we do that by dividing both sides by V. So this P can stand alone. So doing that lets us know that P is equal to nRT over V. So let's impute our variables right now. N is 0.02 multiplied by R, which is 0.0821 multiplied by T, which is 295, all divided by the volume, which is 0.5. So P is equal to, when we say 0.02 multiplied by 0.0821 multiplied by 295. That gives us 0.48439 divided by 0.5. That gives us 0.97 atmospheres. So I'm sure you saw how that was done. Let's move on to the next thing that we have. Alright, so now that we have all of that in place, it's important to know some of the common mistakes you need to watch out for. First things first, you need to be careful about your units. It's important to always check your units before you plug them into the formula. Make sure the units of pressure, the units of volume, the units of temperature, and the gas constants are all compatible. The next is about temperature. You have to always make sure that Kelvin is the unit that is used for measuring temperature. If the temperature is given in degrees Celsius, for instance, you are to convert it into Kelvin by adding 273. So, having said that, here are some practice questions that I'd like you to try out your hands on and comment the answers in the comment section below. And I'd be more than willing to receive them, reply them, and we'll move on together. So, we have the first practice question that says a sealed can of soda has a volume of 0.35 liters, contains 0.15 moles of a gas. If the temperature is 300 Kelvin, what is the pressure inside the can? So go ahead, do that question, and as well handle the second question as well, that says a balloon has a volume of 2.5 liters at 25 degrees Celsius and contains 0.1 moles of helium gas. What is the pressure inside the balloon? So I look forward to seeing your answers in the comment section. With that being said, I want to say a very big thank you if you stuck around till the end of this video. It's bye for now, and as we go, remember there are more videos coming up, so you want to subscribe, like this video, turn on the notification bell icon, so when more stuff like this come out, you'd be the first to be notified. My name is David. Once again, all I do here is take the mystery out of chemistry so chemi can make history. I will see you in the next video.